Alright, so now we're going to look at some examples where we use this first derivative test, this idea of using the derivative to tell us where a function is increasing and decreasing, and where we might have local min and max values. So we're looking to find both local and absolute extrema. So extrema is just a fancy word for the extreme values that refers to the min and the max values. So we're given this function f of x. So the first thing that we're going to need to do is find our derivative. Okay, so this is a pretty simple derivative to find. All right, once we have our derivative, we want to look for critical points. Remember, critical points are points where the derivative is equal to 0 or is undefined. Now, as we look at this 3x squared minus 12, it's never undefined. So if there are critical points, they're going to occur where it's equal to 0. Okay, so as we solve here, we can take out a 3, left with x squared minus 4. That's going to produce x equals plus or minus 2. Okay, so these are our critical points. So think of them as points of interest. Okay, in all likelihood, they're going to end up being a local min and a local max, but sometimes, like we saw, the sign's not always going to change. So what we do is we make a sign diagram. So this is a number line where we're going to do this for our derivative f prime, so we're going to label it. It's important to label because we're also going to be making these for the second derivative. So negative 2 and 2 are our critical points. Okay, so we're going to plop them on our number line. And above here I'm going to put a 0 because the derivative value is 0 for those two x values. So now what we need to do is we need to test some values on each side of those critical points. So to test some values, we're going to plug back into the derivative. Now you can plug back into your original derivative back up here, or I recommend plugging into the factored form of our derivative, which I should have written out as x plus 2, x minus 2. Okay, that led to x equals plus or minus 2. So what we want to do, and this can typically be done mentally, all right, but you want to plug in some points. So let's first focus on to the left of negative 2. So values less than negative 2, something like negative 3. Well, we don't care about this 3 in front. That's always positive. Okay, so we have to plug into this factor and this factor. If I plug in a negative 3 into the first factor, negative 3 plus 2 is going to give me a negative number. And then negative 3 minus 2 is another negative. A negative times a negative will give me a positive. And again, you don't have to show this work up above where I wrote negative times negative. You can do that in your head. Likewise, let's plug in 0. That's something in between negative 2 and positive 2. If I plug in a 0, I'm going to get, again I'm plugging into this factored version of our derivative. I'm going to have a positive times a negative, which is going to produce a negative. Finally, something bigger than 2, like 3 or 3 million, is going to produce a positive times a positive, which is a positive. So now we need to interpret this sign diagram. Notice how our derivative goes from positive to negative, so that means it's going to be increasing, then decreasing. And when I say it, I'm referring to f. Okay, f is going to be increasing, and then it's going to be decreasing, which means right here at negative 2, we're going to have a local max. All right, and then at positive 2, our derivative is going from negative to positive, so it's decreasing, then increasing, so we have a local min. So let's summarize everything that we can conclude from this sign diagram. So here's our summary. It tells us where f is increasing and decreasing, and these are intervals over which that's happening. I've written down the local max and local min x values straight from our sign diagram. So again, if we were to sketch what f might look like, all right, it would be something like this, where it's increasing, it reaches a local max, decreases for a while, hits that local min, and then increases. Okay, so let's make a table since we're looking to also identify any absolute extrema. So recall that in our table here, we're going to put in our critical points of negative 2 and positive 2. All right, and remember, we're trying to figure out where we might have our extrema on f. Okay, all of this work involves the derivative, and the derivative is used to tell us about f. So if you were to plug negative 2 back into this original equation, you would get 11. If you plug in positive 2, you'd get negative 21. And we talked about already how those are the local max and min values. Now, absolute extrema. We're not going to have any of these because if you were to plug in, now we don't have any bounds, right? It's not bounded on an interval. So if you were to plug in something like negative a million, all right, into this original function, okay, you would get something that is very, very small and negative. So something like negative a million might come out for y. Same thing if you were to plug in positive 1,000 or a million, you get something huge for y. So we can conclude that we have no absolute extrema. And this can be supported by our graph by the fact that we have arrows going up and down forever. So there is no bottom point or top point that it reaches over its domain. Okay, it goes down forever on the left side, goes up forever on the right side. So we're talking about its end behavior, okay, on each side there. So here's an example where we don't have any absolute extrema, we just have local extrema. So one of the things I like to do as I shoot these videos is I like to play it back real quick before I upload it, just to try to do a little quality control. And as I was doing that, it occurred to me that I made a mistake. This right here should be a negative 2, not a positive 2. Or perhaps I did it on purpose to make sure you were paying attention. Yeah, that sounds good. I'm going to go with that story. So that's my story, and I'm sticking to it. Okay, one more example. We have another function, this time a little more complicated. It has an e to the x in it. Again, we're looking to find our local and our absolute extrema. So first, we need our derivative. So because we have a product here, we're going to need our product rule. So let's go ahead and find our derivative. So there's our derivative. Recall that the derivative of e to the x is the same thing back, e to the x. Now, we know that we're going to have to set this equal to 0 and solve. We also have to identify any points where it's not defined. All right. Well, looking at this derivative equation, there is nothing that we can't put in for x to get something out for g prime. So there's not going to be any points where the derivative does not exist. Okay. So let's set it equal to 0. And to help us do that, let's factor out a GCF here of e to the x. Okay. Okay, so after we take out e to the x as a GCF, we're left with 2x plus this x squared minus 3. Now we can rearrange these terms and put it in standard form, and then we can factor that quadratic. From there, when we set each of these pieces equal to 0 and solve, we know that we're going to get a negative 3 from that factor and a positive 1. And over on this side, if we were to try to set e to the x equal to 0 and solve, you end up having to take the natural log of 0, which is undefined. That means it's not going to produce any answers on that side. So negative 3 and positive 1, these are our only critical points. Okay, so next we need to make a sign diagram. So we're doing this for g prime. So we're marking off negative 3 and positive 1. Go ahead, hit pause, take a moment, and try to find your signs. So if we do that, you get plus, minus, plus. If you're not sure where that came from, keep in mind that this e to the x here, this is always going to be positive. Think about y. E to the x looks like that, right? It's always positive. So you just had to plug into x plus 3 and x minus 1 to get your signs. Now, I should add here that above negative 3 and positive 1, we have zeros because that's where the derivative is equal to 0. Okay, so we are trying to find the absolute and local extrema on g. So we know that because our function here is increasing and then decreasing, we're going to have a local max at negative 3 and at 1. Because the function is decreasing and then increasing, we're going to have a local min. So let's make a table and summarize what we have. Remember, we're trying to find the absolute highest and the absolute lowest on G. We're using G prime as a tool to help us find the critical points, which we know produce local max and min values. They could also be they could also be an absolute value. So when we plug in -3 into this equation, and again we're going back to the original equation here for G, if you plug in -3, square it, and then subtract 3, you're going to get 6e to the -3, which is the same as 6 over e cubed. That's a modest sized number. E cubed is fairly big, but 6 divided by e cubed, it's going to be something positive. It's not quite 0, but it's something positive. Now, if it were e raised to the 3000, it would basically be 0. But 6 divided by e cubed, let's assume you're not allowed to use a calculator, but if you were, that is approximately 0.299, okay? But without a calculator, we just know that it's something modest in size, something positive, okay? Let's do the same for 1. So here, we're going to get -2e to the first, which is just -2e. Notice this is some negative number. Okay, let's check negative infinity and then positive infinity. Okay, so first, with negative infinity, we are going to plug in something like -1000. If we do that, the first part is big, right? Something huge, and then times e to the negative infinity. Well, that is equal to something big times 1 over e to the positive infinity. Now this 1 over e to the positive infinity is approaching 0, right? Because it's 1 divided by something huge. So that means the whole thing, the whole product, is going to be 0. Likewise, plug in something like 1000. That first factor again, and I'm referring to this equation back up here, right? So you get something big again, and now e to the positive infinity, that's going to give you something that's big overall, so infinity, in other words. So we're trying to determine, in addition to our local max and local min values, do we have an absolute min or max value? So we are comparing these numbers. And really we're comparing this one, since pretend you didn't have a calculator to know it was 0.299. So we're comparing these 4 values. Well, this infinity down here suggests that we have no absolute max, okay, because it goes up forever. And the smallest one that we see is this -2e. Okay, that's clearly a negative number. It's the smallest out of the 4. So that suggests that we have an absolute min at x equals 1. Now, yes, it's true that when x equals 1, it was a local min, but we can further classify it as an absolute min since it's the absolute lowest value. And finally, just to confirm this, if you were to sketch a graph of G using your calculator, what you would see is a function here that levels off at 0. Okay, so as x approaches negative infinity, we talked about how the y value is approaching 0. So that's shown over here on the left side. On the right side, it's going up forever. But right here at +1, this is where we have our absolute min. Okay, and by the way, the absolute min is -2e. Okay, yes, it occurs when x is 1, but the actual absolute min is -2e. That's referring to the y value. And if you're wondering, well, where does the local max show up? That shows up over here, all right, in this neighborhood. If we were to zoom in on this, we would see that it rises up and then comes down a little bit and then approaches that 0. So I didn't draw that very well, but it does reach a high point over here at -3, and then it comes back down and approaches the x-axis as x approaches negative infinity.